Have you ever thought that in this universe, everything can be measured and predicted with absolute precision? That we just need enough tools and information to uncover every mystery? That idea dominated science for centuries, but then a principle emerged, fundamentally challenging our perception of reality. This is Heisenberg's uncertainty principle, a discovery that shook the foundations of classical physics, revealing a captivating beauty of uncertainty at the smallest level of the universe. Welcome to SpaceTime's universe journey of discovery, where we explore the deepest mysteries of the universe. In this video, we will explore Heisenberg's uncertainty principle. Don't forget to subscribe to the channel so you don't miss out on other exciting universe exploration videos. If you find the video interesting and useful, please like and share to support us.
In the 1920s, as physics was undergoing a profound revolution, the German physicist Werner Heisenberg introduced one of the most groundbreaking and controversial concepts, the uncertainty principle. This statement is not merely a limit on human measurement capabilities, but an intrinsic, unbreakable characteristic of the universe itself at the subatomic level. It forces us to accept that absolute certainty is an illusion in the quantum world. Under the gaze of classical physics, every object has a definite position and momentum at all times. If we know an object's initial position and velocity, we can accurately predict its future trajectory. But at the atomic and subatomic levels, this picture completely collapses, giving way to an ambiguous and probabilistic reality where uncertainty is not a flaw, but a hidden beauty, an inherent part of the universe's nature. This has changed the way we perceive everything. Before Heisenberg, scientists believed that with enough information and measurement tools, they could know everything about a physical system. But the uncertainty principle showed that there are pairs of physical quantities that we cannot know precisely at the same time. The most typical example is the position and momentum of a particle. This principle states that we cannot simultaneously determine both the exact position and momentum of a subatomic particle. If we try to measure an electron's position more accurately, then the information about its momentum becomes more imprecise, and vice versa. This is not due to the limitations of our measuring equipment. It's not like you can't accurately measure your height and weight at the same time because you only have one scale and one tape measure. Rather, this is a fundamental limit of nature itself, an invisible wall erected by the universe. To understand better, imagine you want to determine an electron's position. The only way to see an electron is to shine light on it, i.e., shoot photons at it. But an electron is an incredibly tiny and light particle. When a photon collides with an electron, it transfers energy and momentum to the electron, changing the electron's position and momentum. If we use short wavelength, high-energy light, to determine the electron's position more precisely, the photons will transfer greater momentum to the electron, causing its momentum to be severely disturbed. Conversely, if we use long wavelength, low-energy light, to avoid disturbing the electron's momentum too much, that light will not be accurate enough to determine the electron's position in detail. Thus, the act of observation, in a way, interferes and changes the very object being observed. It's like trying to precisely determine the position of a ball floating on water by shooting a jet of water at it. Your action changes the state of the ball. This is a fundamental difference compared to classical physics, where it is assumed that observation does not change the state of an object. The uncertainty principle is often expressed by a famous mathematical formula. Delta x times delta p is greater than or equal to h bar over 2. Here, delta x is the uncertainty in the particle's position, delta p is the uncertainty in the particle's momentum, and h bar is the reduced Planck constant. This formula shows that the product of these two uncertainties must always be greater than or equal to a certain value, never 0.
This value, though very small, is the absolute limit of precision in the quantum universe. Besides the position-momentum pair, the uncertainty principle also applies to other conjugate pairs, such as energy and time. This means that if a system exists for a very short period, its energy will have a large uncertainty. Conversely, if a system exists for a longer period, its energy can be determined more precisely. This has profound applications in particle physics, explaining the temporary existence of virtual particles. One of the biggest consequences of the uncertainty principle is that it completely shattered the notion of determinism in the universe that classical physics had built. Previously, scientists like Laplace had envisioned a universe where every event was predetermined by initial conditions, like a giant clockwork machine. With the uncertainty principle, this idea becomes impossible. We cannot know everything precisely enough to predict the future with absolute certainty, even theoretically. Quantum reality is not a collection of predictable events, but a world of probabilities and possibilities. Einstein himself, who contributed greatly to quantum physics, was uncomfortable with this uncertainty. He famously stated, "God does not play dice with the universe." However, experiments have continuously confirmed the uncertainty principle, making it one of the most solid foundations of quantum mechanics.
Why don't we experience this uncertainty in everyday life? The reason is that Planck's constant is an extremely small value. At the macroscopic level, for large objects like balls, cars, or humans, the uncertainty in their position and momentum is too small to be noticeable. We can treat these objects as having definite positions and momenta without any practical problems. But when we delve into the world of subatomic particles, where mass and size become extremely tiny, quantum effects, including uncertainty, become prominent and govern their behavior. The beauty of uncertainty. This phrase encapsulates a profound truth. It is not just about accepting a limit, but an invitation to explore a richer, more complex reality, where randomness and possibility play a fundamental role. Uncertainty opens the door to creativity in the universe, allowing states to exist and transform in ways that classical physics cannot explain. It shows that the universe is not a pre-programmed machine, but a living entity, always harboring surprises. In philosophy, the uncertainty principle has sparked intense debates about the meaning of reality, the role of consciousness, and free will. If the universe is not entirely predictable, is there room for human free choice? It also raises questions about the very nature of knowledge and the limits of what we can truly know. The applications of the uncertainty principle in modern technology are immense. It is the foundation for the development of quantum technologies, such as quantum computers, quantum cryptography systems, and electron microscopes. These technologies harness quantum effects, including uncertainty, to perform tasks that classical computers cannot, opening new eras for computation and information security.
Electron microscopes, for example, rely on the wave-particle duality of matter, allowing scientists to see structures at the atomic level that ordinary light cannot. This has revolutionized biology and materials science. Einstein's uncertainty principle also helps us better understand the structure of atoms and their stability. If electrons could have both definite position and momentum at the same time, they would be attracted to the nucleus and atoms would collapse. It is this uncertainty that prevents electrons from falling into the nucleus, creating stability for the physical world we live in. Heisenberg's uncertainty principle is a reminder that the universe is far grander than we imagine. It is not merely a physical formula, but a door opening to deep reflections on the nature of reality, the limits of knowledge, and the elusive beauty of existence. It invites us to embrace complexity, randomness, and surprise as indispensable parts of the cosmic tapestry. And in doing so, it makes the universe richer, more mysterious, and perhaps much more beautiful. It is one of the most important milestones in the construction of quantum mechanics, a field that has forever changed how we understand the universe at the smallest scale. Uncertainty at the quantum level not only challenges classical thinking, but also opens up strange and fascinating possibilities about the macroscopic structure of the universe. If a particle can exist in multiple states simultaneously, then is our universe merely one of countless possibilities? This brings us to one of the boldest ideas in modern physics, the multiverse and brain theory. Are there other universes besides ours existing in parallel with different physical laws or even other versions of ourselves? In the next video, we will explore these challenging questions together, learning about multiverse theory, brain theory, and the evidence and arguments scientists are using to unveil the secrets of countless other universes out there. Don't miss that exciting journey into the infinite.